請咗 Innuos 嘅CTO 首席技術官咧嚟到香港，想介紹一下啱啱佢喺上個星期推出咗嘅 Innuos Pulsar。佢真係第一次嘅空運到香港啦，同埋都真係其實出咗大約幾日都冇。上個星期啱啱喺 Espona 出完show 之後，就即刻飛嚟香港就做一個 introduction。Hi, Nuno. Yes, he's back. May I ask some questions about this latest flagship, the Pulsar?
Absolutely. Pulsar is the top of the line of the Pulse series in terms of our network music players. So the series starts with the Pulse Mini, which is a more basic product. So it does have an integrated DAC with digital outputs, coax, optical, and analog outputs, but no integrated linear power supply. So it's a very small, compact streamer to start with the line. Then second in the line, we have the Pulse. And the Pulse is an evolution of the Pulse Mini in the sense that already includes an internal linear power supply as well as a better digital to digital converter. So it provides now AES, optical, and coaxial with a higher grade implementation than a Pulse Mini. Then the Pulsar comes on top of the line, and here we have quite a lot more changes. So the Pulsar is the first product that Innuos does that uses the trickle-down technology from the statement next gen. So it uses the same architecture in terms of having an ARC6 type power supply with active rectification. So what you can see here is a 300 VA toroidal transformer. So that's an oversized transformer that will lower the impedance in terms of the power supply. As you can see, there's actually two outputs that are placed in parallel, again, to reduce the impedance. Because we only use one rail here, but we put them in parallel, so it's almost like you have twice. It's like having twice the gauge of the wire.
Understand.
So then we have the active rectification module that we have here, and then goes into the capacitor bank. So 6 Mundorf caps here, have a much bigger inductor here to provide a blacker background, much better filtering in terms of noise. And then it goes out with a Mundorf silver gold oiled output capacitor. So already a very high grade power supply. So this is similar to what we have. It's like a smaller version of what we have on the statement. So the statement has much larger capacitors and a much larger inductor, and there's 2 of them for separate areas. And then after this, we will have, so this will power the CPU directly, and we will have 2 more regulator stages now here that uses the CX modules provided and designed by Dr. Sean Jacobs. So one of the CX modules is powering an SLC type SSD that's working on the motherboard here. So that further provides a refinement over what you see in the Pulse and the Pulse Mini, as well as having another regulated stage to power, in this case, the digital output module. So this is also a new concept that we are introducing with the Pulsar, because these boards we can actually replace with other modules. So right now, by default, the Pulsar will bring the USB reclocker module. So this is a similar design to what we have on the Phoenix USB and on the statement. It's a bit more simplified because there's a single linear power supply for the entire board instead of having 2 separate linear power supplies like it exists on the Phoenix USB and on the statement. But we are working on having more. So you have different outputs. So for those who wish to have something like AES or even eventually I2S. So this is something that we can work on different boards to replace.
Kind of modular design.
That is correct. Because different people will have different usages of the system. And so some people will prefer the USB, some people will prefer dual AES if they have to connect like to DCS, let's say. Or if they have DACs that support I2S and they want to bypass the entire USB stage of that DAC, then eventually they can do it that way as well. So this is something that we're developing for the moment. The only thing that is available is the USB reclocker module, but this will change in the near future.
That means they will have more digital outputs in future, which is modular, maybe.
Exactly.
I see.
This SSD will last very, very long. It is an industrial grade type SSD, so this will guarantee that your system will be there and it's very, very safe for long-term use.
How will it affect the sound, the sonic performance at the end?
Well, there is a very audible difference in terms of when you actually use the normal TLC versus the SLC. The thing you will notice is a better separation of instruments.
I see.
That's one of the more immediate results because, and what we like about these modules as well is that they are extremely simple. And this is very much in line with the philosophy we have for our designs. Rather than having controllers that are very complicated and perform very complicated algorithms, we prefer something that is simpler, that is more direct, and that it creates less noise in the system. So as you can see, the controller here is quite small. It doesn't have a lot of, it doesn't create heat. So when you use, for instance, M2, the bigger M2 SSDs or PCIe SSDs, they even need heat sinks out of them in order to dissipate the heat. And that's more heat inside the entire system. And the warmer you have the system inside, it will degrade the performance of all the components, so the power supply and all that. They don't like to be very hot.
Just now you mentioned about the CPU we use.
Yes.
It's a low power CPU normally we are using. So what's the advantage of using the low power CPU?
The main advantage that we use with this kind of CPU, we have two approaches to it. It allows us to do better power supplies. That is the main advantage. Because when you have a CPU that requires a lot of current, then you can't have this kind of approach. So for instance, the CX modules that have been designed here, this kind of design will reduce up to 10 times the amount of noise in terms of the TCO lines. But they only work effectively up to 1 amp of current. So if you're providing, let's say, 12 volts, and you're doing 1 amp, there's 12 watts. The TDP for this is 6 watts. So we can
Just
actually...
6 watts?
Yes. So it's very, very low. And what we are looking in this kind of CPU is that there's multiple cores, so that there's divided. But because we don't need very high performance cores, what we need is a lot of cores. So that they can run things separately.
I see.
So in this case, this board, despite being a 6-watt TDP, has 4 independent cores. And it's not hyper-threading, it's actually 4 cores. Because in
real
fact,
core.
there's real cores. So the fact that it doesn't have hyper-threading is also an advantage. Because hyper-threading makes the instructions sometimes have to queue and they have to wait a little bit. So that introduces a bit more weight in latency.
Maybe
in terms
higher
of the
latency, about higher latency or things like that?
That's correct. And in that sense, something like this gives us the benefits in terms of both worlds, so that it's low power, so we can create better power supplies for it. There's enough power for doing the music server functions in the Pulsar, because that doesn't require a lot of CPU to actually do things. And at the same time, so it dissipates less heat inside, it has more cores, so that all combined for us gives us a very good sound quality for something that it's quite compact as well.
So we have an OCXO here.
That's correct.
And that's pretty big comparing with what we saw elsewhere. So what's the difference? What's so special about this module?
The thing about the OCXO clock is that in a lot of cases, people only look at the phase noise. They go to the specs, they go to the spec sheet, and they go there, okay, what is the phase noise at 10 megahertz? What is the phase noise at 100 megahertz? And so on. And this does not tell the whole story. Because these are the tested values for it. Now, you need to see that these are measured in ideal circumstances in laboratories where everything is stable.
Yes.
But the world is not ideal. So what's important is not when you actually put these clocks in real world circumstances where they can get cooling from the convection of the air, where they can be put with hot things underneath, hot things above, you want something that it's more resilient to that. Because the focus of the clock is stability. It needs to be very stable. So there are no deviations in terms of the timing. So what you want there as well is something that can also resist so that to those changes. So it's kept stable. And that's why it has such a big enclosure. Because so this is an oven controlled oscillator. And the size of it makes for a much better way to actually stabilize the temperature inside and to make it more resilient to that. This is also why you see, these dots all around, these holes all around. This is actually a way that we can have less contact surface between the board and the clock, so there's less transfer of heat from the components on the board to the oscillator. So for instance, on this board, we use 3 very ultra-low noise regulators, the LT3045, to power each of the voltage inputs on the chip. So we provide the 1.1, 3.3, and 5 volts, all with independent linear regulators on this board. So these linear regulators also produce a little bit of heat. We don't want that heat to be transferred to the clock. So we isolate that out.
3 more current linear supplies.
That is correct. It's almost like 3 regulator stages that are inside the reclocker
PCB.
itself. Yes, that is correct. So we receive the 5 volts from the main, but then it goes through an additional stage to go directly to the
3 sets of step-down linear power supply.
That's correct. Because we could have easily used a USB chip that just accepts 5 volts and you just connect there and the job done. But the problem is that the chip inside will have switching regulators. So it will need the different ones. So you don't want those switching regulators inside. So what we want is a chip that doesn't have any switching regulators inside and receives all the voltages from outside. So this way we can actually provide the power to it. This is an area that is fundamental to our designs, is to power each component in the best way, in the way that it needs to be powered. So this is the same with the SSD module here. This is powered by a separate power supply. We've tested when we power it through the linear power supply or powered just by the motherboard, which comes from the power supply. So one would think, well, maybe it's not going to make much of a difference. It makes. It is very audible. And it's something that we've tested extensively to do, because for us it would be a lot better just to have less regulation and just a simpler architecture here. But these are something that makes a real difference. So overall in the design, what we went is to say, okay, what are the elements or something like the statement that make the most effect on sound quality? So the statement is far more advanced in terms of having the AVC platform, there's CPU booster modules, there's more power supplies to the clocks. So it's a more evolved server. And obviously it does have storage and ripping and so on. But what we get here is a compact version that gets kind of the factors that make the most difference, and we leave then the other 20 to 10% then that adds a lot of cost to the system and keeps it simple this way.
I see. Thank you. Thank you, Nuno, for the comment and for introducing the Pulsar.
Thank you very much. And if you have the chance, come and have a listen. And I think you will be very surprised with the kind of sound quality that you get of a system like the Pulsar at
Yes.
this range.
We will do. Yeah, thank you.
Thank you.
Yes, thank you.